Hello everyone and welcome to Reinforcement Learning Tutorials. In this tutorial, I will explain the basics of the Q-learning algorithm. Furthermore, I will explain how to implement this important algorithm in Python. To test the performance of the Q-learning algorithm, we use the Cart Pole OpenAI Gym environment that you can see over here. This is basically a pendulum attached to a cart. So this is the cart and this is the pendulum. The goal is to apply horizontal forces either in this direction or in this direction such that the pendulum stays in the vertical position. The animation that you can see over here shows the effect of applying the Q-learning algorithm to this problem. And you can see that the Q-learning algorithm for first, let's say, 200 steps is able to stabilize the inverted pendulum or the cart pole system. The reason why, after a certain number of time steps, the system is not stabilized anymore is simply because I stopped the training process since I wanted to illustrate in relatively short time interval how the Q-learning algorithm works. So after watching this video and repeating all the steps that I will explain, you will obtain a basic understanding of the Q-learning algorithm. Moreover, you will be able to generate this nice animation that shows the effect of the Q-learning algorithm. Before I start, I have to mention the following. The algorithm that I will explain in this video is just a basic algorithm. This algorithm is used as the base of a number of more advanced Q-learning algorithms. For example, in my next video, I will introduce deep Q-learning network that are based on combination of the algorithm presented in this video and machine learning methods such as deep neural networks. So stay tuned. Those of you who are my subscribers or who follow my work know by now that I always create a post that nicely summarizes everything that I will explain in this video. And consequently, here is the post. This post contains graphs, contains thorough explanations, and moreover, it contains Python codes. A link to this post is given in the description below. Also, I have to mention that it took me a significant amount of time, energy, and planning to create this post and the video you're watching. So I kindly ask you to press the like and subscribe buttons. Thank you very much. Okay, so let's start. Before watching this video or reading this tutorial, it's a very good idea that you become familiar with the basic concepts of reinforcement learning. And consequently, over here I prepared two tutorials that are very useful for understanding the material presented in this video. So consequently, you can click over here to get yourself familiar with the cart pole control environment. You can basically understand what a cart pole environment is, how this environment works in the OpenAI Gym, and you can learn how to simulate this environment in Python. Secondly, it's a very good idea that you become familiar with on-policy SARSA temporal difference learning, because this algorithm is very important for understanding the Q-learning algorithm. In fact, the Q-learning algorithm and SARSA algorithms are very similar. And in this tutorial, I explain how to implement the SARSA algorithm on another cool OpenAI G environment that's called Frozen Lake. Consequently, I kindly suggest you that you go over this tutorial. We explain the Q-learning algorithm by using the OpenAI Gym cart pole environment that's illustrated in this figure. You can see that this system consists of a cart, and this cart carries a pendulum or a pole. This pendulum can rotate around this point over here. So you can imagine a pendulum with a bearing attached to the cart. We can push the cart right, or we can push the cart left. The control objective is to keep the pole in the vertical position by applying horizontal actions or forces to the cart. We can apply force in this direction or the force in this direction. And consequently, the action space consists of two actions. Push the cart left, denoted by 0, and push the cart right, denoted by 1. Next, we introduce the observation space or the states. The state vector is four-dimensional. Its entries are x, or the position of the cart, x dot, or the velocity of the cart, theta, or angle of rotation of the pole, and theta dot, or the angular velocity of the pole. The cart position, or x, is in the interval from minus 4.8 to 4.8. The velocity of the cart is in the interval from minus infinity to plus infinity. The pole angle of rotation, that is theta, is in the interval from minus 24 degrees to 24 degrees, and the pole angular velocity, or theta dot, is in the interval from minus infinity to plus infinity. Here, it's very important to emphasize that once we reset the environment, and I will explain you later on how to reset the environment, our system starts from a completely random initial state. The initial state values are chosen uniformly from the interval minus 0.05 to 0.05. This physically means that our pendulum starts from this position, where this angle is very small. Then we should also emphasize that an episode terminates under the following conditions. If the pole angle becomes greater than 12 degrees, then the episode will complete. This means that if the pole rotates for more than 12 degrees, for example, over here the angle is, let's say, 25 degrees, the episode will be finished. Then, if the cart position is greater than 2.4, also the episode will be finished. This means that if the cart reaches the limits of our workspace, the episode will be finished. Also, the episode will be finished if the number of time steps in an episode is greater than 500. Every time we apply an action and the episode is not completed, we obtain a reward of +1. This is because the control objective is to keep the pole in the upright or vertical position. That is, the higher sum of rewards is obtained for longer episodes. This means that we keep the pole in the vertical position for a longer time. So the rewards can be a good measure of how long we keep the pole in the vertical position. If you obtain 500 rewards, this means that for 500 steps you keep the pole in the vertical position. However, if you obtain the sum of rewards 200, this means that for 200 steps you kept the pole in the vertical position. Now we are ready to summarize the Q-learning algorithm. The core of the Q-learning algorithm is an equation for updating the action value function that is usually denoted by capital Q. Here you need to stop for a second and ask yourself the following question. Do I understand what is an action value function? If the answer is negative, you should immediately stop watching this video and you should go back at the top of this tutorial and click on this tutorial that should explain you the on-policy SARSA temporal difference learning. By studying on-policy SARSA temporal difference learning, you will become very much familiar with the action value functions. Okay, so let's go back to the explanation of the Q-learning algorithm. First, we need to initialize the values of the action value function, Q. I will explain how to do that after I present the algorithm. After we initialize the action value function, we need to loop through the training episodes. And in every training episode, we need to perform the steps that are given over here. First, we need to initialize the environment to the initial state denoted by capital S. This means that we start an episode from the state S. Then, for every time step of a single episode, that is, until the terminal state is reached, that is, until the next state, that's usually denoted by S prime, is not the terminal state, we perform these three steps. The first step is to select an action capital A in the state capital S on the basis of the epsilon greedy algorithm. Graphically, this means that in the current state S, we need to select the action A by using the epsilon greedy algorithm. I explained the epsilon greedy algorithm in my tutorial on SARSA temporal difference learning. And here, for completeness of this video tutorial, I will briefly summarize the epsilon greedy algorithm. In order to apply the Q-learning algorithm, we need to define and update in every time step a table storing the values of the action value function. Graphically, this table looks like this. It has many rows, and each row should be uniquely indexed by the state. The table has two columns. The first column corresponds, in our case, to action 0, and the second column corresponds to the action 1. If you have many actions, you will have multiple columns, and every column should be dedicated to the specific action. Every block of this table, for example, let us say the block over here, stores a value. And this value is the value of the action value function. For example, this can be 0.123, and here we can have, let's say, 0.4. So this block is action value function at the state S and under the assumption that the action 0 is taken. In the same manner, the block given over here is the action value function in the state S and under the assumption that the action 1 is chosen. So under the assumption that we define and we maintain such a table, we can apply the epsilon greedy algorithm in order to select the actions. And here's the main idea of the epsilon greedy algorithm. First, we select a real number epsilon that's in the interval from 0 to 1. This is our user-defined parameter. Usually, epsilon should be, let's say, 0.1 or 0.2. Then, in every step, that is in every time step, we draw a random number from the interval 0 to 1. If this number is smaller than epsilon, and remember that the epsilon is predefined parameter, we select actions in the current state randomly. That is, we can select with the equal probability action 0 or action 1. That is, we don't care about the actual entries of this table. Okay, to repeat this procedure once more, we first draw a random number from the interval 0 to 1, and then if this number is smaller than epsilon, we randomly select either 0 or 1. That is, we don't care about the precise values of the action value functions. On the other hand, if p is larger than epsilon, where epsilon, keep in mind, can be 0.1, 0.2, or a relatively small number, then we apply the greedy algorithm for the selection of the proper action. In this case, that is, if for the action 0, the action value function is 0.123, and if for the action 1, the action value is 0.4, we will select the action that produces the maximum value of the action value function. And that's why this algorithm is called greedy, because we select the action that produces the maximal value of the action value function. To illustrate this idea once more, let us assume that our current state S is over here and that we have two action value functions. We have, let's say, 0.51 and 0.39. Then let us assume that we selected randomly a real number p from the interval 0 to 1, and let us assume that p is larger than epsilon. Then we apply the greedy algorithm in order to select the proper action. In this case, we will select the action 0 because in our current state S, action 0 produces the maximal value of the action value function. And again, this is the main idea of the greedy algorithm. Okay, so we are in the current state S. We selected the action A by using the epsilon greedy algorithm. Then we apply such an action to the environment and we observe the reward R. This action will lead us to the next state that's usually denoted by S prime. If this state, that is, if the next state is not the terminal state, we proceed further. In the third step, we need to update the action value functions. Under the assumption that the next state, capital S prime, is not the terminal state, that is the state that ends the episode, we update the action value function by using this formula over here. Let us illustrate this formula graphically. First, let us define again the Q table. The Q table has rows, and every row corresponds to the particular state. It has two columns in our case. The first column corresponds to the action 0, the second column corresponds to the action 1. And let us assume that this row over here corresponds to the current state S, and that this row over here corresponds to the next state, S prime. Next, let us assign some random values to this Q table. For example, let this value be 0.1, this value 0.3. Over here, let us assume 0.4, and over here, let us assume 0.2. Let us assume that A is equal to 0. And let us assume that the reward is equal to +1. So let us see how to apply this formula. Basically, this formula is telling us that q s comma 0, that is this value over here, that corresponds to q s comma 0, because 0 is the action, should be updated like this. The previous value of q s comma 0 is 0.1 plus alpha, and remember that alpha is a parameter that we need to select a priori, that is before we initialize the algorithm. Usually alpha can be a relatively small number and it's called a step size. So this is just a constant that you choose. Then the reward is 1. This is the reward that we obtained going from the state S to the state S prime, plus gamma, and gamma has usually different names. It's basically a discount rate. You can assume that gamma is equal to 1 over here, times Q max. So let us see what is Q max. Q max is defined over here. Q max is the maximum value of the action value function in the state S prime. So let us analyze the state S prime given over here, and we simply need to select the maximal value, and the maximum value is 0.4. And over here we need to add the minus sign, and we need to basically write down here 0.1, since 0.1 corresponds to qs, 0, the previous value. And this is how we update qs, 0. So in the next time step, this will be not anymore 0.1. Instead, it will be equal to this number that's defined for alpha and gamma. And that's the whole story. On the other hand, if the next state S prime is the terminal state, that is, if this state is equal to the state that ends the episode, then by definition we have that qs prime comma a prime is equal to 0, and we use this formula to update the action value functions. And that's it. These two formulas are the main formulas for updating the action value functions. And this is how we train our algorithm. And then after we update the action value functions, we set the current state to be equal to the next state, and then we again go to the step number 1. And in the step number 1, we select the action A in the state S on the basis of the epsilon greedy algorithm. And we repeat this many times until we reach the end of the episode. Once S becomes the terminal state, one training episode is completed, and then we start with the second training episode. That is, we again initialize the environment to the initial state, and we repeat the whole procedure. Once the algorithm is executed for a desired number of episodes, we compute the action value function. That is, we will have a table with the final values of the action value functions. Then, when we want to illustrate the performance of the algorithm, in every state, we select the action by using the greedy algorithm. That is, we are not using anymore the epsilon approach. We don't have any exploration. We only use the greedy approach. And this is our final learned policy. The final learned policy is a greedy policy based on the learned values of the action value function. Here we need to explain how to initialize the algorithm. That is, we need to explain how to initialize the action value functions. In the classical textbook on reinforcement learning, an introduction by MIT Press, it's written that qs, a can be initialized arbitrarily, except the values of qs, a for the state s that are the terminal state. If S is a terminal state, then we have the following initialization. We need to assign Q S, A, where S is the terminal state, to 0. However, in the case of the above stated algorithm, we never actually use QS, A values when the state S is a terminal state. This is because of the two if statements in the step 3 of the algorithm. That is, I always check if my next state is a terminal state, and then I adjust the formula for updating the action value functions. Consequently, we can completely arbitrarily initialize the algorithm. That is, we can arbitrarily or randomly initialize the action value functions. Okay, everything is fine until now. It's not difficult to understand the Q-learning algorithm. However, here we reached one big problem. And the problem can be explained like this. So let us go back and let us consider our inverted pendulum or the cart pole system. Let us remember the states. The states are the position x, the velocity x dot, the pole angle of rotation denoted by theta, and the pole angular velocity denoted by theta dot. We can define the state vector x, x dot, theta, and theta dot. And this is equal to S. In order to apply the Q-learning algorithm, we need to define, maintain, and update a table storing the action value functions. And remember that the number of rows of this table should be equal to the number of possible states. So for example, this can be state 1, state 2, state 3, state 4, 5, 6, 7, 8, and 9. And then again, we have columns corresponding to the action 0. Action 0 is push the cart left. Then we have another column corresponding to the action push the cart right. And here is the big problem and a big challenge. Our state space, that is, the possible values that x, x dot, theta, and theta dot can take, is infinite. That is, there are infinite possible states. For example, we can have a state vector 0.1 minus 0.123 minus 0.21, 0.3. And there are infinite combinations that these entries can take. Consequently, this means that our tables storing the action value functions need to have an infinite number of rows. And of course, this is impossible. You cannot define, update, and store a table having an infinite number of rows. And this is a big challenge in applying. So we need to somehow discretize our state space. And this is a very important step when applying the Q-learning algorithm in this particular form. We need to discretize the state space. Here I have to mention the following. In my next video, I will explain the deep Q networks. And deep Q networks are not based on updating the tables. Instead, deep Q networks are based on using neural networks to learn the action value functions. And they have one big advantage over the approach that I present in this video. That is, we only need to train the deep Q network. However, here we need to discretize the state space and we need to store action values in a finite table. Next, we explain how to discretize the state space. Let us focus on the position x, and let us assume that x can be an interval from 0 to 1. Let us make a small illustration over here. This is our cart, and this is its position. Let us say that we measure the position from 0. And let us say that the maximum value of the position is 1. So let us discretize this state entry. We will discretize this state entry by dividing this interval into 4 segments. The segments will be bounded by these values: 0.25, 0.5, 0.75, and the final segment will end at 1. So this is the segment 0, this is the segment 1, this is the segment 2, and this is the segment 3. Notice here that I'm using the Python notation, and in Python notation, the indices start from 0. So let us assume that our value of x is 0.6. This means that x belongs to the segment number 2. That is, to this segment, we assign the index that is denoted over here. On the other hand, let us assume that x is 0.213. This corresponds to the discrete index of 0. So for any x in the interval from 0 to 1, we can assign the indices 0, 1, 2, and 3. And in this way, we can discretize the state's space. That is, to store any value of x in the interval from 0 to 1, we will need 4 indices: 0, 1, 2, and 3. We can perform this discretization for other state variables. In this way, we can assign to every continuous state a set of discrete indices: ix, ix dot, I theta, and I theta dot. That is, we transform the continuous space into a discrete space where every entry in the discrete space is denoted by the combination of indices. Let us see the graphical illustration of this concept. This is our Q table over here. And this Q table has another column, and this column corresponds to the state index. This means that index of x is 0, index of x dot is 0, index of theta is 0, and index of theta dot is 0. For example, over here, this set of indices corresponds that the index of x is 7, index of x dot is 1, index of theta is 5, and index of 2 is theta dot. And in this way, we transformed a continuous state space into a discretized state space that can have a finite number of entries. And in this way, we can define a finite Q action value table that stores all the possible states. Of course, two different states will be mapped into the same row. However, we don't care about that. We can always finally discretize x, x dot theta, and theta dot in order to make sure that states that are relatively far away from each other are mapped into different indices. By using the Q table defined in this way, we can run the algorithm. First, we observe the state S. That is, we observe position, velocity, angle of rotation, and angular velocity of our system. And let us say that these values are given over here. For example, they can be 0.1, 0.2, 0.35, and 0.1. Then On the basis of this continuous state, we run one function that will spit out the set of indices ix dot, I theta, and I theta dot. For example, 0, 2, 1, 2. And then these set of indices uniquely define a row of our Q table. For example, this can be a row over here. And in this way, we can uniquely define action value functions and we can run the algorithm. And finally, let us explain the Python codes. Over here, I will explain you the class that I defined that implements the Q-learning algorithm. The class name is Q-learning, and this code can be accessed on my GitHub page. All the links will be provided in the description below. So let us analyze this class. Here's our init function. This is our environment. It's an OpenAI environment. This is our step size. Gamma is another parameter that's called discount rate. Usually I set gamma to 1. Epsilon is the parameter for the epsilon greedy algorithm. It can be 0.1 or 0.2. Number of episodes is the number of episodes. That is the number of training episodes. For example, you can select this number to be 10,000, 20,000, or 30,000. Next, let us explain this important parameter called the number of bins. Number of bins is a four-dimensional list that defines the number of grid points for state discretization. That is, this list contains number of bins for every state entry. Since we have 4 entries, this list has 4 elements. That is, the first element is the number of bins for cart position, the second is the number of bins for cart velocity, and the third and fourth one are the number of bins for pole angle and for pole angular velocity. So let us illustrate this on an example. Let us say that number of bins is 4, 2, 2, 3. And I'm just giving these numbers as example. In practice, you would probably need much denser mesh. You will need probably 30, 30, for example, 40, and 50, or something similar. However, here for illustration, I'm just giving small numbers so I can graphically illustrate them. So this means that for the discretization of X, we have 4 bins, 2, 3, 4. So we have 0, 1, 2, 3, 4 bins. For the discretization of X dot, we basically have 2 bins, 0 and 1. For the discretization of theta, we have 2 bins, again 0 and 1. And for the discretization of theta dot, we have 3 bins, 0, 1, and 2. Next, I need to explain these two parameters, lower bound and upper bounds. Lower bounds are the bounds for discretization. It's basically a list with 4 entries. Lower bounds on cart position, cart velocity, pole angle, and pole angular velocity. In the same manner, the upper bounds defines upper bounds on the cart position, cart velocity, pole angle, and pole angular velocity. Now you can stop me here and you can ask me the following question. Why did you introduce these bounds? And the answer is very much straightforward. Let us go back and let us analyze our environment. The cart position is in the interval from minus 4.8 to 4.8, and we simply set these bounds. However, the cart velocity, denoted by x dot, is in the interval from minus infinity to plus infinity. So you cannot numerically set a bound to be minus infinity and plus infinity. We shrink these bounds. I arbitrarily assign these bounds by running several experiments, several random experiments, by randomly selecting control actions and observing typical values of x dot. And I set the maximum and minimum bounds on x dot that appear in my simulation, and I choose these bounds. Otherwise, if you, let's say you have from minus 10 million to 10 million and you put only 40 bins, you will have very poor discretization. That's why you need to shrink these bounds. Pole angle of rotation is not problematic since it's in the interval from minus 24 to 24. You can also shrink this bound since the episode ends at minus 12 and 12. And again, the pole angular velocity suffers from the same problem as the car velocity, and consequently we need to shrink these bounds. Again, run a few simulations, see where these bounds are in practice, and shrink them accordingly. Now that we understand the input parameters, we can proceed further. Here I only assign the variables. Here I introduce another list that stores the sum of rewards per episode. Here I'm storing the sum of rewards in order to quantify the convergence of the algorithm. In the first, let's say, 1,000 of episodes, you will have small numbers here, 30, 40, and then later on these numbers will go to 100, 200, 300, etc. This is our Q matrix. I simply initialize it as a random matrix with uniform entries in the interval from 0 to 1. Again, going back to our explanation, this matrix is the matrix that's given over here. It's basically multidimensional matrix, and I define its shape or its size accordingly. We have number of bins 0, that is numbers of bins for x discretization, number of bins for x dot discretization, number of bins for theta discretization, number of bins for theta dot discretization. These are basically the indices, and then I have two columns on top of that corresponding to the action number, and the action number is equal to basically 2 since we have two actions. And that's it. That's our init function. Next, we need to define a function that for a given state returns a discretized indices. So what do we do over here? We observe our state vector, and over here I define position, velocity, angle, and angular velocity. Then I simply perform discretization, and I return this list over here. Here is the graphical explanation of this function. This function takes as an input argument the continuous state S, and it produces a tuple of indices corresponding to the discretization of this state. For example, the indices can be 1, 2, 3, and 0. These indices are used to access the rows or the entries of our Q matrix that stores the action value functions. In order to make this video as short as possible, I will not explain this function in more details. Just as a brief comment, this function is very easy for understanding and it's a homework for you. So try to understand in more details this function. Let us proceed. Next, I defined a function for selecting the control actions. The name of the function is select action. It takes two parameters. The first input parameter is the state, and this is the state in the continuous domain. And the second parameter is the index of the current episode. Now you can stop me for a second over here and ask me the following question. Why do I need an index? Well, you need an index because on the basis of the index of the current episode, we will choose the strategy for selecting the control actions. For example, during first 500 episodes, we select actions completely randomly. We do that in order to ensure that we explore the environment And this is very important. So for the first 500 episodes, I will not use the epsilon greedy approach. I will simply randomly select my control actions in order to explore my environment and to see typical values of the action value functions. Then, after 500 of training episodes, I will select the control actions by using the epsilon greedy approach. So here's what happens. I select a random number, and if my index of the training episode is larger than 7,000, I will slowly decrease my epsilon. This is very important because after some time you have more faith in the current values of the action value functions, and you have more faith in your greedy policy, and then you slowly decrease the epsilon value in order to decrease exploration. So this part over here is not active for the first 7,000 of training episodes. Now, going back to this random number selection, we basically test if this random number is smaller than epsilon. If it's smaller than epsilon, we completely randomly choose the action. And this is the epsilon choice, right? It's not a greedy choice. Otherwise, if this random number is larger than epsilon, then we perform the greedy approach. To perform the greedy approach, we basically need to do something like this. We need to call the function return index state, the function that we defined previously. This function takes state, the current state, and returns the index. And then here we basically access the corresponding row of our Q matrix. So again, we take the state, we obtain the index of such a state, and then we access the corresponding row. And this procedure is coded over here. This is the row that we select, and then we simply over here choose the action that produces the maximum action value function. Notice here that I have this random choice because you can have the following scenario. You can have that, for example, two action values have the same value, let's say 1 and 1, which is unlikely that will happen in practice. However, you still need to have some form of safeguard against this phenomena, and then you will simply randomly select actions, since it doesn't matter if it's action 1 or action 0. This function is the core of our class, and this function implements the Q-learning algorithm. Over here, we loop through the training episodes. This list over here stores all the rewards obtained during a single episode. Over here, we reset the environment. Remember that when we reset the environment starts from a random initial condition. And remember from the beginning of this video that all the state space variables take values from -0.05 to 0.05. This physically means that our pole starts an episode from a very small angle, theta. Let us proceed with the explanation of this function. Over here, we print the current episode. Over here, we set the terminal state to false. This flag over here is used to denote the terminal state. Over here, we simulate time steps. This while loop over here iterates through the time steps of a single episode, and it ends when we reach the terminal state. First, we take the current state and we return the discrete index of that state. Then we take the current state and we select the action. Depending on the index of this episode, the actions can be completely random or the actions can be selected by using the epsilon greedy approach. I explained this previously. Then we step, that is, we take the computed action and we apply it to the environment. We return the next state, the reward, and this Boolean flag that's equal to false if the next state, that is, if this state is not equal to terminal state, and it's equal to true if the state S prime, that is the next state, is equal to the terminal state. Then we append the obtained reward to the list, and then on the basis of the state S prime, we compute the discrete index corresponding to the state S prime. So these two indices are used to access certain row of our Q matrix, that is the matrix that stores the action value functions. Over here, we implement the two equations for updating the action value function. And to remind you, these two equations are given over here. Then, after we update the action value functions, that is, after we update the Q matrix entries, we simply set the current state to the next state. That is, state S for the next time step is equal to the next state. And once the while loop completes, we simply append the sum of the rewards obtained in the simulation episodes. And that's it. That's the core of the Q learning algorithm. After the learning process is completed, we learned or we estimated the entries of the Q matrix. And the Q matrix stores the action value functions. The next step is to simulate the optimal policy. That is, on the basis of this matrix that's being trained, if I can say it like that, we need to simulate the learned policy. And we do it over here. We create a cart pole environment, we reset the environment, we render the environment. Since I want to create a simulation, and I will create a simulation that you have seen at the beginning of this video. I select the time step, so 1000, and over here I simply store the rewards obtained during a simulation. Then I simply propagate through the time steps. I print the time index. I select actions by using the greedy approach. Notice here that I said the greedy approach because I want to simulate the optimal policy. I don't want to perform any training, that is, I don't need an epsilon parameter, and I'm simply applying the greedy policy. Then I append the obtained rewards. I pose my simulation such that I can successfully render the environment, and over here, if the simulation is completed, I simply break the loop and I return the obtained rewards and my environment so I can successfully close it. And the final step is to define a function that will simulate a random control strategy. The function defined over here will randomly select actions during time steps. So what's the purpose of this function? The role of this function is very important because we need to compare our greedy approach and our learned policy with something that's completely random. If a random control strategy performs better than our trained system, then we know that we did not train the system properly. That is, if the sum of rewards obtained by using this function is larger than the sum of rewards obtained by using our greedy approach and our trained system, then we did not do the job correctly and we need to retrain our system. So what do I do over here? I create another environment, I reset the environment, and over here I simply simulate episodes and I randomly sample my action space and I apply these random actions to my environment. I observe the response, and on the basis of this observed response, I calculate the rewards and I sum these rewards to see the total sum of rewards. After you define the class, you need to save the file. In my case, the name of the file is functions.py. Then over here, I've wrote a driver code that explains how to use this class. So let us explain this driver code. First, I import the gym environment. You can also import the gymnasium environment. The gymnasium environment is an updated version of the gym environment and it's being actively maintained. Next, I import the NumPy library, I import time, and I import the plotting tools. Finally, I need to import my class from the file functions, and the name of the class is QLearning. Here, I create my environment and I reset my environment. Next, I need to set the input parameters for my class. Over here, I access the bounds in my environment. I simply call .observation_space.height to get the upper bounds, and over here I'm getting the lower bounds. And here I manually set the lower bound for the cart velocity to be -3 and the upper bound for the cart velocity to be 3. Similarly, for the pole angle velocity I set -10 and the pole angle velocity max I set 10. This is because these variables corresponding to cart velocity and pole angle velocity, that is the mean and max value, are -infinity to +infinity, -infinity to +infinity, and as I mentioned previously, this is not good, so you need to manually assign these variables. And over here I set the upper bounds and the lower bounds, that is I modify these upper bounds and lower bounds, and I keep the lower bounds and upper bounds for the position and for theta to be equal to default values returned by these two parameters, high and low. Then I define number of bins for discretization. I choose 30 for discretization of position, velocity, theta and theta dot, and I set my number of bins list. Here I define the parameters. Alpha 0.1 is the step size. This is the discount rate of 1. Epsilon is the greedy parameter. It's 0.2, and number of episodes is 15,000. You can, for example, choose 15,000, 20,000, 30,000. Over here, I create an object of the class QLearning and I set the parameters. After that, I run the QLearning algorithm. That is, I run the function simulate episodes. This function will go through episodes and it will train, that is, it will learn the values of the Q matrix. I have a relatively new computer with 64 GB of RAM and relatively powerful processor. However, on my computer it takes at least 20 minutes to run 15,000 of training episodes, and I'm not going to repeat this training process over here in order to make this video as short as possible. Instead, I will again create animation of the final learned strategy. So let's create this animation. This for loop over here will generate this animation, and in every step of this for loop, I simply call the function simulate learned strategy. This function uses the Q matrix values and the greedy approach to simulate the final learned strategy. You can see that I can maybe stabilize the pole for 200 or 250 time steps. This is because I stopped my training process after 15,000 episodes. You can continue the training process for, let's say, 30,000 episodes and you will obtain much better results. However, let us compare this strategy with a random strategy and let's see what happens. Over here, we can plot the sum of rewards obtained during the training process. And the complete graph is given over here. On the x-axis, we see the episode number, and on the y-axis, we see the sum of rewards. We can see that initially, the sum of rewards are relatively small during, let's say, first 500 or 1000 episodes, and we can see over time the sum of rewards obtained during an episode increases. Next, let us compare this optimal control strategy, that is the optimal policy, with a completely random policy. We can do that by invoking the function simulate random strategy, and this function implements random selection of actions. And over here, I generated the histogram by using these code lines. This histogram shows the distribution of rewards obtained by applying a random control strategy. And we can see that typically the sum of rewards is 20 or even 10 or 15 if you apply a random strategy. And by comparing this graph with this graph, that is the graph showing the optimal policy, we can see that our optimal policy performs much better than random policy, because over here we see that the rewards are, let's say, in the order 200, and the random rewards, or actually the random actions, produce rewards that are 20 or 30 per training episode. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.